Now you know the story of thalidomide, and you know the importance of cis and trans and left-hand and right-handed molecules. And in this video, we're going to expand that a little bit more. We're going to go back to this definition of a chiral center. What really is a chiral center? How can we identify it? What is a chiral carbon? Because it's organic and we typically look at carbon-based compounds. And how can we use a chiral carbon to determine if a molecule is left-handed or right-handed? And keep in mind, I also told you we're going to keep it simple. For the most part, we're going to be working with very small molecules, but folks, larger molecules can also have chiral centers. There's no difference there. So we just apply the rules that we learned here with simple molecules to big ones as well. But on the test, on Blackboard, they're going to keep it pretty simple, pretty focused as far as left hand and right hand goes. So let me go back and start at chiral center. Okay, so a chiral center is also called, another term that we can use, an asymmetric carbon, if we're looking at chiral carbons, or an asymmetric center. It doesn't have to be carbon-based. Well, what does asymmetry mean to you? It means it's not the same, right? If I say something's asymmetrical, then that means, it's not the same on both sides. It doesn't look all neat and tidy. It's kind of skewed a little bit. Well, chiral centers or chiral carbons are asymmetric carbons, and basically in the world of organic, what that means is that there's 4 different groups. All 4 have to be different. Okay, well, what if 2 of them are the same, like 2 hydrogens? No, that's not chiral. That's how clear-cut that definition is. 4 different groups have to be on a carbon in order for this thing to be classified as chiral. So the next question that you might have, well, what about sp2 carbons? Okay, so for instance, a carbon double bonded to a carbon. Well, keep in mind that if that carbon's double bonded, there's only 1 bond that can happen here and 1 bond that can happen there, and that's a total of 4. Is that 4 different things? No, it's not. There's not 4 different things attached to that carbon. Again, that's how clear-cut this definition is. It has to be 4 different atoms onto a carbon. Only then do we worry about left hand and right hand. If it doesn't have 4 different groups, it doesn't have a left hand and right hand version. That's how simple this definition is going to be for us in the beginning, and we're really going to keep that definition all the way through. Okay, well, what about sp carbons? Folks, the story's the same. All right, an sp carbon is a C triple bond to another carbon, and that other carbon has 1 more bond to give it a total of 4. There's not 4 different groups attached to that carbon. You know good and well if a double bond's not going to be classified as chiral, then a triple bond's not going to be classified as chiral either. 4 groups. 4 groups. Now, I keep using this term center and this term carbon interchangeably, because that's really what we're going to put our focus on. But keep in mind that things like nitrogens, they can also be classified as carbons, right? Things like phosphorus, those can also be classified as chiral. So we're not going to pay too much attention to these, though, but I do want you to understand that the world of chirality and stereoisomer and stereochemistry expands outside of the carbon world. We're just going to stick with carbon. Again, back to basics. So, let me give you a nice, clean, pretty example to start off with. Let's say that we have a carbon, we have 4 things on it, and we have a hydrogen, and a chlorine, and a bromine, and maybe an OH group. Is that chiral? Yes. Okay, well, if you can answer that type of question, you can answer those questions in Blackboard, and you can answer those questions on my test. Really, in the beginning, this is what it's all about. Identifying a carbon that has 4 different things on it. All right, so there's a very clear-cut description right there. There we go. So if I have another carbon with 4 things, and let's say I have a chlorine and a bromine and maybe an OH and maybe another chlorine here, is that chiral? And the answer here is, of course, no. It's not. It's not. And the reason is because there's 2 chlorines on that carbon. So because of that, it doesn't meet the definition of chirality. Again, if you can answer that type of question, good news for you. There's going to be questions like that on the assignments and the test. Well, we're kind of going to go a little bit bigger. Okay, these are very simple little cute molecules, right? I mean, it's like Polly Pocket molecules. Well, we need to go a little bit bigger, meaning in carbon chain. Well, what if we had like a carbon and a carbon and a carbon and a carbon and a carbon, and then maybe on this carbon I had an OH group, and maybe down here I had a chlorine. 2 functional groups on it. Is that chiral? Well, I know this one's not going to be chiral because this is CH3. 3 hydrogens, wrong. It doesn't meet the definition. This carbon here, it needs 2 more hydrogens. Well, there's 2 hydrogens there. No chiral carbon at all. The same story is going to happen here. Next to the last carbon's got 2 hydrogen, and then the very last one has 3 hydrogens. Nothing. No, those carbons can't be chiral. The one that we're going to question, though, is going to be this one, because it looks like there's maybe 4 different possibilities, 4 different groups that could be attached to that carbon. I see an OH group up here, and then I see a chlorine down here. Those are 2 different groups. And then to the left, I see an ethyl group, a CH2 and a CH3. I take the whole thing. Okay, so this is an ethyl group. And then over here to the right-hand side, I see a CH2 and another CH3. And this is also an ethyl group. So because of that, there's not 4 different groups attached to that carbon. 2 of these groups are ethyl groups. Folks, we treat ethyl groups just like chlorines and bromines and OHs. They're the same. So it doesn't meet the definition of chirality. However, if I erase one of these carbons, look at this, and I put a CH3 there, now we're talking. Now we're in business. This is an ethyl group, and it's a methyl group, and it's an OH group, and it's a Cl group. There are 4 different groups attached onto that carbon, which makes that carbon chiral. Well, I didn't have to erase one. I could have added one, right? I could have added another carbon onto the chain. Now we have an ethyl and a propyl and a chloro and a hydroxy, or an OH group. 4 different groups, isn't it? Therefore, that carbon is now a chiral carbon. So once we identify a chiral carbon, we have to understand this. A chiral carbon leads to left-hand and right-hand notations. I have not really given you the formal designation for those yet. I'm just writing L for left and R for right, but that's not really what we use. Okay? So these are going to be chiral. We have a chiral carbon. That carbon has a left-handed version and a right-handed version, and I'm going to be expected to draw the left-handed version of that molecule and to draw the right-handed version of that molecule. Also, what that means is that a chiral center has a non-superimposable mirror image. You remember that example problem that we did with the alphabet, right? Or the image that we showed of the forks and the chairs and all of that other silly stuff. All of this is wrapped up together in the world of stereochemistry. All right, so let's take a look at an image. This is probably shown in your textbook. And this image shows a carbon that is here. And this carbon has 4 different groups. I don't care what those groups are. You shouldn't care what those groups are. Right? I mean, they're just representing these as different colors. Different colors represents different groups. Who cares? Well, we got a purple one, and we got a pink one, and we have a green one, and we have a yellow one. And folks, if this does have a chiral carbon, and it does. There's 4 different groups. And if we take the mirror image, flip this sucker around, there we go. There's our new one. If you had a model kit and you made these 2 models exactly the way that they look on the screen right now, that model kit is 3-dimensional. It lets you see this perspective maybe a little bit more. And if you made molecule number 1, and if you made molecule number 2, and you took those 2 molecules in your model kit, and you turned them around, and you try to perfectly match those up together to make them the same image, pointing in the same orientation and the same direction, you would not be able to do it. I know it's very tempting to look at this and say, no, the only thing that you got to do is just kind of take this and move it over here, and then, you know, as you turn it, this pink one is going to kind of turn this way, and that would be over on the right-hand side. So it looks like the pink would match, and the green would match, and the purple one up here would match, right? So it's the same molecule. No, it's not. And the reason that that doesn't work is because you also have this yellow one too that you forgot about. The yellow one in the first diagram is pointed backward. It's pointed away from you. If you took this molecule on the right-hand side and you turned it the way that you want to, that's very tempting to say my purple matches, then my pink would match, and my green would match because they would be on the same side. That's great. But your yellow one would not. The yellow one would point forward, not behind. So therefore, they are different orientations. If they're different orientations, then we have to treat them as different molecules. They have different names when you get down to the nitty-gritty of it all. So these are non-superimposable mirror images. And if that is very difficult for you to kind of visually see, then you really do probably need a model kit and play around with that model kit a little bit. Or watch maybe some videos on YouTube. And if I can find some of those, I'll pull them up and I'll put them into the Blackboard site so that way you can see these a little bit better. All right? If you can see the models, and if you can see people twist and turning them to try to get them to match, realizing that they can't match no matter how they turn them, then you can kind of grasp this concept a little bit better, a little bit faster, and a little bit easier. All right, so let's take a look at some example problems that we might see. All right, how complicated are these questions going to get? All right, so let's take CH3, and then CH, and then CH2, and then CH3, and then a Br here. And the question could say, identify the chiral carbons if there are any. Okay, so there might not be any at all. And here's our first example. I can quickly go through and cancel 3 of these out. I'll just look at the hydrogen count. This one has 3 hydrogens, that one has 2 hydrogen, that one has 3 hydrogen. Can't do them. Those are not chiral, folks. Sorry. It's as easy as that. So I've got 1 carbon that's left. Is this carbon a chiral carbon? All right, well, let's take a look at it. I have a carbon. To the left, I have a methyl group. To the right, I have a ethyl group. To the bottom, I have a bromo group. And then on that carbon, I also have this hydrogen. Folks, there are 4 different groups that are there. So, yes, that does have a chiral carbon. That means that at that point in the molecule, there could be a left-hand version and a right-hand version that would represent that molecule. And we can draw those on a sheet of paper and represent them that way. And we're going to have to learn how to do that. But before you can go that far, you have to be able to identify a chiral carbon or not. Right? If you cannot identify a chiral carbon, then how are you going to go any further? You can't do it. So that's why we start with these types of examples. Okay, so let's take a look at another. we'll do CH3, CH2, CH2, CH, CH2, 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 CH3, and then an OH here. So my question to you is, does this have a chiral carbon? Yes or no? Well, once more, I can go through and out quite a few of them. I just look at the hydrogens. If there's more than one hydrogen, I know it's not going to be chiral. There's not 4 different groups on it. So this one's a no, and that one's a no, and this one's a no, and that one's a no, and this one's a no, and that one's a no, and this one's a no. Look how easy that was. Even though this was a bigger molecule, don't let it scare you. Don't let it intimidate you. It's as easy as all the others. So the questionable one would be the carbon that we haven't X'd out yet. Does that really have 4 different groups? So I see the OH group and I see the hydrogen. Those are 2 different groups. I know that. So we're on to something at least for now. And then to the left, I'm going to look at this whole thing, and this is a propyl group, right? 1, 2, 3. And then to the right, this is a butyl group. 1, 2, 3, 4. Oh, okay. So that means there's 4 different groups here. Propyl, butyl, hydrogen, and OH. Notice what I did. I'm keeping the whole thing. I'm not just going to the neighbor, meaning I'm not going left and say, hey, that's a CH2, and then I just don't go right and say, oh, that's a CH2. No, those are the same. That's not what we do. We include the whole groups here, especially in the straight chains. In the straight chains, we include the whole groups whenever possible. So we've got 1 chiral carbon, and this 1 chiral carbon means that at this position, we have a left-handed version and a right-handed version, and we're going to have to be able to draw those versions on a sheet of paper. All right, so let's do one more. This time, let's do a CH3, CH, CH2, CH, CH2, CH3, and let's point a CH3 down there, and let's put a CH3 up here. So does this molecule have any chiral carbon? Well, you know what I'm going to do. Let's cross out the ones we know for sure are not. That's the easiest ones, right? So if they have more than 1 hydrogen, we know absolutely not. No chiral carbon at all, period. All right, so this one is a no. And this CH2, that's a no. This CH2 is a no-no. This CH3 is a no-no. And that CH3 down there is a no-no. This one up here at the top, CH3, that one's a no-no. So it looks like I have 2 carbons this time, right? Can it have more than 1 chiral carbon? Of course it can. Of course. Yes. It makes our job a little bit more complicated, but it could have 2 chiral carbons. So if both of these are chiral, so be it. We identify both of them as chiral and we move on, if that's all that the question wants us to do. So let's look at the first one to the left. Is this a chiral carbon, yes or no? So I see the hydrogen on here, and I see a methyl group on here. I look right-handed, and I see this really 1, 2, 3, 4, 5. Is that a sec-pentyl? No, that's not a sec-pentyl. Is that an isopentyl? No, that's not an isopentyl either. So this is just an isomer of a pentyl group, and we could formally name that IUPAC if we wanted to, but that's not the purpose of these problems. And then up on top, oh, I see another methyl group. I have a methyl group up here, and I have a methyl group to the left. So that makes this a carbon. No chirality that's assigned to that carbon at all. So now we just have one left that we have to test. Is that carbon going to be chiral? Yes or no? A molecule might not have any, and this might be one of them. So let's see. If I look at this carbon, I see an ethyl group to the right-hand side. I see a methyl group to the bottom, so that's different. And then to the left, I kind of see this isobutyl group, right? There's my iso unit. There's 4 carbons in total. So there's an isobutyl unit. And then that carbon also has a hydrogen. Folks, there are 4 different groups. That's right here. So the answer is yes, this does have a chiral carbon, and that chiral carbon is right here. So that means that at that position only, we can have a left-handed turn or we can have a right-handed turn. And once more, we have to be able to draw these on a sheet of paper, identify them, and represent them the proper way. Now, let's take a look at a molecule like this. This molecule is tetracycline. Tetracycline is an antibiotic. So when I was in high school, I had problems with my face. Acne everywhere. Acne breakouts would continue to happen. So what did they decide to do? The dermatologist put me on tetracycline for months and months and months, and then that led into 1 and 2 years, and all of a sudden I was on an antibiotic for 24 months or longer? This was crazy. What happens when you take someone away from an antibiotic? All kinds of stomach and intestinal problems begin to happen. You've basically eaten all of the good and bad bacteria up. All right, so that was an issue. That's the story with antibiotics. Antibiotics is the world of organic chemistry. So if you want to go to pharmacy school, if you want to go to medical school, folks, this is whole part of organic, and that's why they make you take these types of classes. So this is the structure of tetracycline. Tetra, how many does that mean? 4. Okay, so we're on to something. 4. Cyc. Well, from organic, you would know that probably means cyclo. Cyclo rings. Oh, look. 1, 2, 3, 4. Who would have thought? Tetracycline. Well, off of these groups, I have nitrogens, which are amines. We know that now. We have OH groups, which are alcohols, and we know that now. We have double bond O's, which are carbonyls, and we know that now. And look at this. We've got all of these wedges, and we have all of these solid wedges, dashed wedges. We now know maybe what that means. It's pointed away and it's pointed toward us. Look, all the wonderful things of organic chemistry wrapped up into just a simple antibiotic known as tetracycline. We also see double bonds involved. We know that these are alkanes. And folks, I now know if I react this with HCl, what would happen? If I react it with Br2, what would happen? If I reacted it with maybe a little bit of mercury, what would happen? If I reacted this with H2 platinum, what would happen? All of these things are wrapped up into one little package. And I kept telling you, and I will keep telling you, organic is a build-up process. We're just putting the pieces together. That's all we're doing. So this question says, how many carbons are chiral? And they don't want you to look at all of them. They want you to look at only the ones that they have numbered. That's it. All right. So let's go through. Let's take a look. Number 1, is that chiral? No, it's not. And the reason is because there's 3 hydrogens on it. I automatically knew that just by looking at it. So let's look at carbon number 2. Is that one chiral? No, it's not. And it's the same reason as what was with carbon number 1. So now let's look at carbon number 3. Right there. Is that carbon chiral? Yes or no? So this is how we do this. It looks like if I go right-handed, this is a carbon with a double bond and an OH group. And if I go left-handed, that is a carbon that is not double bonded and it doesn't have an OH group. Automatically, they're different. Automatically, they're different. So those are 2 different groups. I don't have to go any further than that. Pointed up is this nitrogen, which is our 3rd different group. And then the 4th bond. Where is that 4th bond? It's not drawn. Well, what's it understood to be? You got it. It's understood to be a hydrogen. And folks, there is my 4th group, and all 4 are different. So number 3, the answer is ding ding. That one is a chiral carbon. That's how we identify those. All right, so now let's take a look at carbon number 4. Carbon number 4 is going to be this one right here. With carbon number 4, I'm going to do the same thing. I'm going to go left, and I see a carbon with a double bond and an OH. I'm going to go right, and I see a carbon with a double bond O. Folks, they're already automatically different. Already. So these are two different groups at least. And then if I go up, I see a carbon, and the only thing on it are just single bonds and a hydrogen. So that is a third different group that's pointed up. My fourth group is the OH group. That is also different than the others. This had an OH, but that was on a carbon with a double bond. So carbon, double bond, OH, group 1. Carbon, double bond, O, group 2. Then the carbon, group 3. And then the OH, group 4. So the answer is yes. Number 4 is a chiral carbon. Let's look at number 5. Carbon number 5 is up here to the left. 3 hydrogens. That was a very easy one. I enjoy those. You should enjoy those too. It makes my life a little bit easier with these. Carbon number 6, right here. Let's take a look at carbon number 6. I go left, and that is a carbon that has a double bond on it, right? If I go right, this is a carbon, and it doesn't have a double bond. They're automatically different. I don't have to go any further. So 2 different groups already. My third different group is a carbon with 3 hydrogens, and that's where that one stops. And then my fourth group is my OH group. So, by definition, number 6 is a chiral carbon. There we go. Number 7, this one. Let's look at it. I come down. Here's a carbon with a double bond on it. I go left. There's a carbon with a methyl and an alcohol group on it. That's different. I go right, and this is a carbon with just 2 hydrogens on it, so that's different. And then where's my fourth? I don't have one, do I? Yes, I do. Never forget that basic rule. That fourth one is a simple hydrogen. Folks, that also has 4 different groups. So number 7 is a chiral carbon. Now let's take a look at number 8. Here's carbon number 8 that they want me to look at. Is that chiral? Yes or no? I go left, I see a carbon with single bonds. I go right, I see a carbon with single bonds. Are those the same? Well, I can keep trucking it on out if that's what I want to do, and I can keep comparing them, but number 8 is going to be simpler than that. And the reason is because there's only 2 bonds that are represented. I should have not even looked at the left-hand and right-hand side. And the reason is because carbon number 8 also has 2 bonds that are not drawn, and each one of those are to hydrogens. Folks, there's 2 H's there. It automatically does not qualify for a chiral carbon. So I can quickly mark that one out and move on to question number 9. So with carbon number 9, we have this here. To the left, I have a carbon with some hydrogens. Down below, I have a carbon with an OH group and some other things. That's different. I move to the right-hand side. That's a carbon with a nitrogen on it, so that's different. And then finally, I also have a hydrogen on it. So the answer here is yes, there's 4 different groups. So out of these 9 carbons that they wanted me to look at, 1, 2, 3, 4, 5 of them are going to be chiral. The other 4 are achiral. So keep that in mind. Achiral is the term that they use for something that has not yet has 4 groups. What else can I say about this structure? Look at where your chiral carbons are. You want a quicker shortcut? This is how we do it. Remember, I told you the importance of wedges, right? Solid wedges and dashed wedges. Look at this carbon 3. What do you see on it? Dashed. automatically it's probably chiral. If it wasn't chiral, they probably wouldn't even go through the trouble of doing that. They're giving you some orientation about it. So it's a very good sign that it is a chiral carbon. Does that mean that it is every single time? Not necessarily. But it's a very good indicator that we do have a chiral carbon at play, because they're trying to show me stereochemistry. And right now they're trying to tell me this nitrogen with those two methyl groups are pointed away from me. Carbon number 4, the OH group's pointed away. I see a dash bond. Very good indicator, chirality is at play. Carbon number 9, same thing. They're pointing the hydrogen away from me. They're giving me a dashed wedge. Again, very good sign. Chirality is at play. Number 6, they give me a dashed and a solid wedge, don't they? Look at that. OH is pointed toward me. CH3 is pointed away from me. Again, they're drawing the wedges on that carbon, which might be a very good indicator that it could be a chiral carbon. The only one that really didn't have it was carbon number 7. Carbon number 7, they did not draw a dashed wedge or a solid wedge on it, but folks, we still identified it as a chiral carbon. So this is why I'm saying they're good indicators, but it's not something that I'm going to use as a go-to feature to completely identify them. That's not what we do with those wedges, okay? So if I was looking at a clean screen, and let's erase all of this marking, the first thing that I would do is I would look at this molecule and go, oh, look, there's a dashed, here's a dashed, there's a dashed, here's a dashed and a solid wedge. Those are very good indicators that they might be carbon. Notice the term that I used, chiral carbons. So let's check those first. But we still have to go through and check all the others. Because if we only looked at that and that was it, folks, I would miss carbon number 7, wouldn't I? I would not pick up carbon 7 on my radar. But carbon number 7 was a chiral carbon by our definition. All right, so that's where this video is going to stop. Hopefully you feel a little bit better about identifying chiral carbons, because once more, we're going to have to go through this scenario again and again and again in order to draw these molecules and to name these molecules the proper way when stereoisomers are concerned.